Hi and welcome to another episode from Spiral Physics Education. So in this episode we're going to be looking at velocity time graphs, and we're going to be looking at how to interpret the motion given data from velocity time graphs. We're going to be looking at how to calculate the acceleration from those graphs and also how to calculate the distance travelled. So to get the most out of this lesson, it would be really helpful if you knew about scalars and vectors, that you knew how to calculate acceleration, and that you also knew how to calculate the gradient from a straight line. And if you're not sure of how to do any of those, please do check out some of the other videos on the channel. So let's have a look at the vocabulary of velocity time graphs. And because of the way that we use velocity time graphs, velocity being first and time being second in that order, that tells us which axis on the graph that we draw each of them. And the first physical quantity goes on the y-axis. So what we have here is velocity on the y-axis and time on the x-axis, just like we did with displacement time graphs. So if we're looking at our graph paper like this, we will put velocity on the y-axis and time on the x-axis, and we might get a shape like that. So let's have a look at calculating gradient, which is really a really important skill in physics. So if we look at a simple graph for a velocity time graph for an object, and let's have a look at calculating the acceleration and see what we get from that. So when we're doing calculation of acceleration, we always mark out a triangle. So always do this and try and make that triangle as big as possible to reduce uncertainties. And we're going to identify the vertical rise of that and the horizontal run of that triangle. And the bit of information that we need to know is that gradient is rise divided by run. So if we look at the rise, well, the rise is actually the vertical rise, which is change in velocity. And the run, well, that's going to be how long it takes for that change in velocity in terms of time. So actually we've got change in velocity over time. And if you recall, change in velocity over time is acceleration. So the gradient and the acceleration for a velocity time graph are exactly the same. So anytime you get given a velocity time graph, you have to calculate the acceleration, calculate the gradient. So let's have a look at describing motion of different types of shapes that you might get provided in an exam. So here we've got a very basic shape for a velocity time graph. And what we're thinking here is that, well, the gradient is constant, and that means that the acceleration is constant. And the gradient, well, it's quite small, so that means the acceleration is small. So we've got a small constant acceleration. Let's change it around slightly. The gradient is constant, but the gradient is larger. So the acceleration is constant and the acceleration is larger. So we've got a large constant acceleration. And for this one, go through the same thought process. Constant gradient, that means the constant acceleration. The gradient is 0, so the acceleration is 0, which means this is moving at a constant speed. Slightly different shape, same thought process. The gradient is increasing, the acceleration is increasing. We can't say anything else about that. And for this shape, same thought process again. I can see that it's, the gradient is decreasing. That means the acceleration is decreasing. We can't say anything else about it. So look at this one, same thought process, constant gradient. That means it's a constant acceleration. Also thinking, well, it's negative, so that means the acceleration is negative. I need an extra thought process here. What does negative acceleration mean? Well, that means deceleration. So this is a constant deceleration for this object. So let's have a look at actually calculating some accelerations from graph examples. So here we've got an example of an object with some data on there. And what we have to remember is that when we're trying to calculate acceleration, we need to write down that we're going to do something with the gradient. So here we've got acceleration is rise over run, which is the gradient. So we need to identify the rise, which is, I'm identifying this point here, so it's 12 meters per second. And the run for that is 15 seconds. So I can put rise over run is 12 over 15, I get 0.8. But I've got to remember the units. So that's 0.8 meters per second squared. So let's have a look at describing the motion of a very common shape graph here at GCSE and IGCSE. And the best thing to do here is to break it down into 3 different sections rather than try to do it all in one go. So the first section goes from 0 to 5 seconds, the second section from 5 to 12 seconds, and then we've got from 12 to 15 seconds. And that makes it much easier for us to describe what's going on. So we're going to describe the motion of the whole graph, but break it into those 3 sections. So between 0 and 5 seconds, what we can say is that it's a constant gradient, and therefore it's a constant acceleration. And we can even calculate it, and I've calculated there as 3.2, but do check how to do that yourselves. Second section between 5 and 12 seconds, well, the constant gradient again, but the gradient is 0, so the acceleration is 0, and it's a constant speed of 16 meters per second. And then the final section, 12 to 15 seconds, it's a constant gradient again, but it's negative, so that means it's constantly decelerating, or it's a constant negative acceleration. So we can either say that it's a negative acceleration of minus 4 meters per second squared, or a deceleration of 4 meters per second squared. And also that it comes to rest after 15 seconds. So let's have a look at being able to describe the motion of this one. This comes up quite a lot in exams as well, and students generally find this shape graph difficult to describe. So what we can say there is that the gradient is decreasing with time. We can also say the acceleration is decreasing because that gradient is decreasing. And if we look, we might be able to estimate that right at the beginning, the gradient right at the beginning of that graph is around about 4. So that we could say that the initial acceleration is 4 meters per second squared. And we can also say that right at the end, the gradient is 0, and therefore right at the end, the acceleration is 0, i.e. it ends up moving at a constant speed of 16 meters per second. So let's have a look at how to calculate the distance given a graph, and this is something where students make a great deal of errors because they forget how to calculate distance if they are given a velocity time graph. So let's say we've got this shape graph, and we're going to look at the area under that shape. So if we look at the area under, that will be the velocity times height, i.e. just the shape of that shaded area. And if we were to look at the area under and look at the equation velocity times time, we might be able to realise that velocity times time is also equal to distance. If you remember that velocity is distance or displacement divided by time. So the key thing here is that area under the graph is actually equal to the distance travelled. So whenever you get a velocity time graph, and underneath that graph there's a question that says calculate the area, calculate the distance travelled, always look to calculate the area under. Don't do any other calculations first. So the area under is the distance travelled. So let's have a look at another shape. So let's have a look at not a constant speed, but one where there's constant acceleration, and how we can calculate the distance travelled here. Well, again, we look at shape, and the area under here is a triangle. So it's half base times height to calculate the area under, and the area under is the distance travelled. So this one is half the base, half of the time, times by the velocity, or the maximum velocity. So just remember that the different shapes are going to have different areas underneath. So let's have a look at a question in an exam that might actually incorporate those 3 different shapes. So let's say we've got a shape here, and what we're going to do is we're going to calculate the distance travelled in that first section. So what we need to remember is that it's the area under the graph. In this case it's a triangle in that section A, and we've got to remember that for the area of a triangle it's half base times height. So half times 5, which is 5 seconds, times by 16 will give you the distance travelled. So the distance travelled in that area is 40 meters. Do check out how to do that properly though. let's have a look at section B. Well, section B, well, that's a rectangle. We've got to remember that the distance for that section is the area under. In this case, we're looking at a rectangle. So this is just base times height. So if we calculate the base times height, the base we've got to remember is for section B only, which means we've got to do 12 minus 5 to calculate the base. But the height is still 16 meters per second. So we get 112 meters for the distance travelled there. And for the last section then, we've got to look at that shape, and it's a triangle again. So the area under the graph this time is a triangle, so we're going to use half the base times the height. Remember, it's just for section C, so the base is 15 minus 12 seconds. So we're doing half times 3 times 16, which is 24 meters for that last one. And then what we could do is they could ask what's the total distance travelled, and then you just add them all up and you get the total distance travelled. But remember, area under. Look for the area under whenever you get a velocity time graph and you're asked to calculate the distance. So I hope you found this episode useful in terms of improving your understanding of velocity time graphs. Do subscribe to the channel for other videos on how to improve your physics understanding in your physics grade, and I shall see you next time on Spiral Physics Education. I was in the middle of doing something then. You just keep coming in and trying to make a pest of yourself, don't you? Hey? What's going on? You're a bit lonely. Hey? You are. I know. Come to treat. Come to treat. Come to licky licks. Is that what you're after? Is that right?